在没管那个脸上的那个。
All right. Hello, everyone. So I know that people have been having issues with the attendance. Emily has kindly joined us. She's sitting over here. If you have any issues with the attendance and the iClicker, please let Emily know and we'll try and address it. With that said, happy Chinese New Year for those who celebrate that. If not, happy Tuesday. Today, it's our pleasure to have Dr. Bruce Hart to give us a presentation on a lot of very interesting work, I think, that's going on, looking at the feasibility of carbon storage in Southern Ontario. And Bruce does come from the Earth Science Department, but I think this whole idea of carbon storage ties in very intimately with a lot of concepts here in civil engineering, both in terms of environmental engineering, thinking about the flow and the permeability, as well as you can call it geotechnical or structural, in terms of thinking of the stresses and the integrity of the rocks in the subsurface. Dr. Bruce Hart received his PhD from Western in the 90s, I believe. And then he went on to be an assistant professor and then associate professor at McGill before heading to the oil industry in Austin, Texas. I think now he's happily back in Canada and working on all sorts of interesting retirement projects. So with that said, I'd first like to note that please keep your voices down, avoid whispering when you can. That sound does carry forward. We can hear you if you're whispering all the way in the back, okay? But all that, welcome, Bruce. The floor is yours.
And I'm known to give the evil eye, up in front of classes, people are whispering. Give the evil eye. Yeah, so it's my pleasure to be here. As Bing was saying, I moved back to Canada after working in the oil industry and down in Texas for 12 years as a researcher. When I moved back here, within about a year moving back here during peak COVID, I got started working on carbon capture and storage projects here in Southern Ontario. What I found is that the skill set that I picked up in the oil industry is kind of unique in this area. As you will see, there has been an oil and gas community in Ontario for some time, but it's small. And this is going to be a really big operation. And so somehow I've gotten dragged into this as much as I'd like to be retired and spend all my time climbing around on outcrops and doing things that geologists do. What I'll be presenting today is presented in two venues. One is a paper that just came out in the International Journal of Greenhouse Gas Control, if you're familiar with that. It's about carbon capture and storage in Ontario and a way of studying carbon capture and storage. And then I was also involved in a research project that led to something known as a roadmap for carbon capture and storage in Southern Ontario. And this is the thing on the right. So I'll be mostly presenting stuff that's in either of these two volumes, and I'll let you know if you want a copy of either of these things, just let me know and we can arrange that. Why do we need carbon capture and storage? Well, I mean, obviously we want to have green energy. We don't want to burn fossil fuels anymore. We want green energy. But when you look at each windmill, what you see is that each windmill is built, and it depends on the type of windmill and everything, but each windmill contains about 250 tons of steel. There's about 800 tons of concrete, mostly for the base, so these things don't fall over, and there's a whole bunch of plastic in there, mostly in the non-recyclable blades. So if we want these to replace fossil fuels, and not just here in Southern Ontario, but anywhere in the world, we need steel mills, we need cement plants. Just keep that in mind as we go through this presentation. So what we'll be talking about are 5 Ws of carbon capture and storage in Southern Ontario. But why do we need it? Why do we need it globally? Why do we need it here in Southern Ontario? What is carbon capture and storage? Who in Southern Ontario is interested in this kind of stuff? When do we need it? And where are we going to put this stuff? And when we get into the where are we going to put this stuff, that's when I'm going to really start talking about the geology. And if you're good, if nobody falls asleep, if not too many people talk, I've got a special bonus W for you about what's coming up in the next couple of years. So why do we need carbon capture and storage? Links between carbon dioxide and global warming are well established. People don't dispute that. We as humanity generate a lot of carbon dioxide in everything we do. The vessels that import coffee, the vessels that transport the material that goes into our cell phones, absolutely everything we do generates carbon, is based on some sort of fossil fuel consumption. This is a graph from the source down, you see down on the right, that shows global carbon dioxide emissions in gigatons per year, starting back in 1800 when things had to be estimated, and going into the post-World War II era, when everybody starts getting cars, everybody wants to start having nice warm houses, everybody starts wanting to have imported food and everything. And you can see what happens to carbon dioxide emissions. We need to bring that down, right? So people start getting serious about reducing carbon dioxide emissions, and it's not happening right yet. But if you take the trend that goes from 2003 to 2013, you take that 10-year trend and extrapolate it on into the future, you see what's going to happen. That's not good news. People start reducing their carbon emissions. If you look at the rate from 2013 to 2018, that 5-year period, you see we've slowed down our carbon emissions, the growth of our carbon emissions. We've slowed down the growth of our carbon emissions. Notice how I'm saying that. We haven't reduced them. If we're to meet the goal of reducing our carbon emissions by 50% by the year 2050, that's what we have to do. It's going to take more than just reducing the amount of times we drive, having electric vehicles. We need to do something really, really serious. And the IPCC recognizes that carbon capture and storage is one of the things that we really need to do as humanity to reduce our carbon footprint, not to slow the growth. So what is carbon capture and storage? Well, the idea is that we're going to take point sources of carbon dioxide, significant point sources of carbon dioxide, things like industrial plants, power plants, and so on. And instead of letting the carbon dioxide go up into the atmosphere, we're going to capture it somehow and put it down into the ground. But we want to make sure the carbon dioxide stays down there for thousands of years. So we call this geologic sequestration. We're going to put it in rocks. We want to make sure the carbon dioxide doesn't come back up to the surface. And the two things that are the most likely targets for these things are either depleted oil and gas reservoirs. So oil and gas reservoirs where you know there's porosity and permeability, you know you can store gas in it because you've gotten gas out of it. Or things known as saline aquifers, and I'll talk about what those are in a second here coming up. So depleted hydrocarbon reservoirs. Imagine you've got some sort of oil and gas reservoir. You've gotten all the oil out of it that you're going to get out of it. You've got a source of CO2. Instead of letting the CO2 come up into the atmosphere, you pump it down into the ground. It spreads out through this old oil and gas reservoir, and it goes away. One of the problems with that, though, is the possibility that if you've got these old oil and gas wells that go down there, potentially, if they're not sealed up, potentially the carbon dioxide could leak back up to the surface. So you might have a leaky seal because of what people have done to it in the past. It's still something that people look at. Another possibility is to take a source of CO2 and just pump it into some sort of porous rock unit that has never acted as an oil and gas reservoir. There's no wells that go into this thing. It's just a bunch of rock that's got porosity, and in the subsurface, porosity's always got water in it. There's always water in it, so you call it an aquifer, even though nobody's going to drink out of this stuff. And as you get down a couple kilometers into the ground, the water becomes salty. So you call these things saline aquifers. Notice groundwater, the aquifers that people are going to get used for drinking water are way up shallow. One of the advantages of this is that by pumping it way down into the ground, it's not going to come back up to the surface. It's not going to interfere with people's drinking water. It's not going to interfere with what's going on at the surface. Wow, that's interesting. There are carbon storage facilities in the world that are already in operation. There are a bunch more planned. Ontario has been forgotten since about 2008. At the time, the provincial government decided that carbon capture and storage was basically a way of allowing people to generate electricity using coal-fired generating plants or natural gas or something. 2008, the provincial government said, we don't want any of that. We're not going to need carbon capture and storage. So they stopped funding research on it. Another thing that sometimes you hear people talk about, and they say they want to shut down carbon capture and storage because of this, is something called, that's more technically correct by saying carbon capture utilization and storage. So that and the idea is that, and you hear about this out west in the heavy oil areas or in other parts of the world, the idea is that if you pump CO2 into an oil reservoir, where the oil has gotten sort of hard to get out, maybe it's viscous oil, you pump CO2 into an oil reservoir, the CO2 reacts with the oil, makes the oil less viscous and easier to pump out. So at some level, you're pumping the carbon dioxide into the ground, but it's allowing you to produce more oil. There's a lot of people who confuse this with carbon capture and storage. This is carbon capture utilization and storage. We're just talking about taking CO2 into the ground, putting it into the ground and leaving it there. Who's interested in this stuff in Southern Ontario? If you haven't noticed, Southern Ontario's Canada's industrial heartland. I'm from Hamilton. I grew up working in places where a lot of my friends, a lot of my family worked in steel mills or various other types of factories. And when you look at who's emitting the point sources of carbon dioxide in Southern Ontario, what you see is by far manufacturing is the biggest point source emitter of carbon dioxide in Southern Ontario. There's utilities. Not much electricity is generated in Ontario by burning natural gas. Some is. And there's a variety of other things, but manufacturing is the key thing. We're in an economy that is based on manufacturing. We're in part of the country that's based on manufacturing. In fact, nearly 750,000 people in Southern Ontario work in the manufacturing sector. That's not including all the people who work in the banking industries and all the other things, the spin-off industries, right? You shut down manufacturing, put 750,000 people out of a job, the spin-offs, consequences of that are going to be devastating. In addition to with manufacturing, we've got a problem here in Southern Ontario that a lot of the industries are what's known as hard to abate industries. And what that means is that it's hard to reduce the carbon dioxide emissions for one of two reasons. Number one is maybe you're generating carbon dioxide just by doing the process itself. So an example here is the cement industry. Cement industry, you take CaCO3 limestone, so you quarry limestone, you heat it up in a furnace, you generate CaO, which is the lime, which is what you're going to use in the cement, but you generate carbon dioxide as well. For every ton of cement you generate a ton of CO2, and there's absolutely nothing you can do about it because that's what you're doing. That's the chemical reaction you're doing. So this cement industry is a really nice example of a hard to abate industry. If we want cement so that we can generate windmills, we're going to be doing this. Another type of hard to abate industry is an industry where there's really no economic alternative to generating the heat that's needed to get the process going. And an example of that are steel mills. If you're using what's known as making a steel from a primary source, you got a primary steel mill. What you're doing is you're taking iron ore that's mined somewhere, taking that rock, melting it, separating out the iron ore, and then you put into the steel making process, and then you've got this leftover stuff called slag. Right now, the only way of generating the heat that allows you to do this in an economic sense without shutting down the industry is using something known as coke, which is coal that's been baked. As you bake the coal, you generate methane. As you burn the coal, you generate CO2. If we want steel to build windmills, we're going to generate CO2, and there's nothing we can do about it for right now. If you look at a map that shows where these 18 of the province's biggest point source emitters, they're in this area. Hamilton, steel mills, North Shore of Lake Erie, steel mills and refineries, Sarnia, where there's a lot of petrochemical plants and so on. Cement plants are all around here. And I've got pipelines on, I'm showing pipelines on my map as well, because if we want to transport the CO2 from these point sources to someplace, we're going to put them underground. That CO2 is going to go through a pipeline. We got a need, and we've got above ground infrastructure. Question is, do we have stuff, what we need underground? When do we need this stuff? We, the royal we, as in Southern Ontario. 2021, federal government signs an agreement, establishes a deadline to reduce greenhouse gas emissions by 40 to 45% relative to 2005 levels. To do that, they're going to raise the carbon tax from $50 a ton to $170 a ton. That's 6 years from now. The steel mill, the steel industries and the steel mills in Hamilton and along the North Shore of Lake Erie, if the cement plants that work in this area, if the refineries work in this area, don't have a way of getting CO2, reducing their CO2 emissions significantly, they're going to go out of business. They're going to shut down. They're going to move elsewhere. So Southern Ontario, we still need to build windmills. We'll be buying steel that's built somewhere else. So you hear people talk about, we're going to do, one potential outcome is that Southern Ontario is going to decarbonize by deindustrializing. Well, let's get rid of the industries and we've solved our problem, right? You're putting 750,000 people out of work, plus all the spin-off jobs. Politically, that's a no starter, right? That's not going to happen. There's a workflow for sanctioning carbon sequestration plants. You spend about a year selecting sites, places, exploring, doing the subsurface geology exploration to try and find places where that might work. And then you go through a characterization step, a development step, an operation step, and so on. These are the estimates of how long each one of these steps takes. We need to get there in 6 years. Or we're going to be carbonized by deindustrialized. When? Now, yesterday. So this is what I've been working on for the past year and a half, trying to figure out, are there places underground here in Southern Ontario that have the right geology for us to put CO2? Now I'm going to get into the rock part. What you need are what I've called carbon sequestration geosystems, rocks down in the ground that have 3 characteristics. One is they've got porosity, they've got pore space that you can put the CO2 in, they've got permeability, which means that you can inject the CO2 in at sufficient rates. The second thing that you need is you need to make sure that the CO2 will not escape up to the surface. You need some sort of trap, stuff that's going to keep the CO2 down on the ground for thousands of years. And then finally, if you pump CO2 into the ground, you're changing the subsurface pressure regime. Maybe you're going to generate earthquakes. You don't want that to happen. So geologists, I've got to look for places that satisfy these 3 criteria. Things to avoid. For pumping CO2 into the ground, we want to make sure it doesn't leak to the surface, right? The other thing we want to make, one of the other things we want to do is make sure that if we're pumping CO2 into the ground and we're pumping it near existing faults that might be buried, we may not be able to see them up on the surface. By changing the stress regime around these faults, maybe we're going to reactivate them. Maybe that's going to generate seismicity. And when you hear about fracking and earthquakes, especially down in the States, usually it's not the fracking itself, it's the disposal, the wastewater that's generated by the oil and gas production. So water comes up to the surface with oil. You got to do something with the water because it's very salty. So people pump it back down into the ground, and that changes pressures. One of the other things we have to think about is that we want to find porous and permeable rocks that are at least 800 meters below the surface, because at the pressures and temperatures that you find about at least 800 meters below the surface, the CO2 goes into what's known as the supercritical state. It's got the viscosity of a fluid. It's tiny, tiny, tiny. So you can put more of it into the ground. So we can find porous and permeable rocks that are going to generate earthquakes that are going to trap the CO2 into the ground. We've got to make sure that we're at least 800 meters below the surface. How do you do that? Use the same tools that you use if you're exploring for oil and gas. You got to characterize the subsurface. You got to do exploration. You got to figure out what rocks are down underground. What their properties are. So there's a workflow. You folks aren't geologists, so we'll kind of skip through this. But this is basically the same type of workflow that you would use for oil and gas exploration. In the carbon capture and storage world, this takes about a year. And this is stuff I've already done. So let's look at what I found. First of all, you need data. If you're going to explore what's underground, you need data. I'm not sure most people recognize it, but understand this, but there's been oil and gas production from Southern Ontario since the late 1800s. It's been small potatoes, oil and gas production compared to what you find in the Middle East or in the US or even Alberta. But there's been oil and gas production in this part of the world since the late 1800s. Red would be gas wells, green would be oil wells. There's over 20,000 wells that have been drilled. A lot of these were drilled in the 1940s and 30s and even older, and they don't have a lot of data. But anything that's kind of from about 1960 on, a couple thousand of them, give us information about what's down in the subsurface. When you do that, what you can see is that down below us, there's some structure that's hidden. So how many people have been up by Huntsville or, up in, you've seen the Canadian Shield, right? The Canadian Shield is buried down below us. And if you look at the top of the Canadian, the Precambrian Shield, what you see is there's a high area here below Kitchener-Waterloo. There's a low area below us here. Then you get off into the Detroit area and things rise up again. Things sink off down into Michigan. Things sink off down into the Appalachian Basin. There's this big arch basically that runs below us here, and here we are about there in London. Not a lot of faulting, not a lot of mountain building. Nothing's really affected this area in the past about 600 million years. So that's good. There won't be a lot of faults that might allow the carbon dioxide to come back up to the surface. If you want to visualize what this might look like, here we are in London. Here's the 401 heading down into Windsor. Down below us is the top of the Precambrian Shield, this big arch that extends down below us. Things drop off down into Ohio and New York. Things drop down off into Michigan. There's this big high area that runs right underneath southwestern Ontario. All the rocks in this area are what we geologists would call Paleozoic rocks, which means they're old, a couple 100 million years. They're limestones and shales and dolomites and sandstones. They're all sedimentary rocks above the Precambrian, that are sitting above the Precambrian Shield. And what we geologists use to characterize the subsurface is well logs. So if you've ever looked at, done any geotechnical work, you've looked at cone penetrometer tests, or you've looked at electrical logs or various other types of things. Oil and gas industry uses very similar concepts, but we log the subsurface down to 2 or 3 or 4 kilometers depth. And these logs tell us what the rocks are. This well, these logs come from a well down near Port Stanley, along the north shore of Lake Erie. There's a variety of different rock types. You see, there's Devonian rocks in these dark green colors are mostly limestones. There's these Silurian, that's a age of rocks that contains limestone, sandstones, and even some salt. So you hear about salt mines and things up in the Sarnia area. There's a big thick section of shale. There's a big thick section of limestone. And then down at the very bottom are these sandstones that we call Cambrian age sandstones. And those are the things that we're going to really focus on. So taking this log, which part of the rock should we focus on? Should we focus on limestone? Should we focus on shales? Should we focus on dolomite? Should we focus on sandstones? Well, the oil and gas industry, up until now, has collected a lot of data that tells us about the properties of the rocks. Two things, among the things they measure are the porosity, how much pore space there is, and something known as the permeability, which is basically how easy is it to push fluids or gas through the rocks. This graph here on the left shows porosity and permeability for limestones and dolomites. This graph on the right shows the same thing for sandstones. The sandstones on average have much higher porosity, which means you can put more carbon dioxide into them. And on average, they have much higher permeability, which means it's going to be easier to put the carbon dioxide in there in the first place. We want to focus on sandstones. So we're looking at the rocks below us here in London. We want to find sandstones. Well, where are there sandstones? Coming back here, Devonian is mostly a limestone. The Silurian's got a mix of sandstones and shales and limestones. What about the sandstones? There's something known as the whirlpool sandstone, which has produced a lot of gas. Well, typically a lot of gas in southern Ontario. Anybody from Hamilton? Stony Creek. You go out to the west, you go out to the east end of Hamilton, you go up along the escarpment, and you can find this place here, Devil's Punch Bowl. You can see the sandstone bed that's maybe as high as this wall is here. In the subsurface, that's produced a bunch of gas over the past 100 plus years. The red areas here show where it's produced that gas. And the colors in the map show how deeply that's buried below the surface. So there's been a lot of natural gas production from these Silurian rocks along the north shore of Lake Erie, even drilling, even production from Lake Erie. I don't know if you know it, but there's been offshore exploration in Lake Erie for 50, 60 years. The problem is it's all very shallow. None of this is below 800 meters. The sandstones, they're permeable, they're porous, but they're not deeply buried enough. What that means is our whirlpool sandstone isn't going to make it. What that leaves are these rocks we call Cambrian, because that's how old they are. Come from the Cambrian period. They're the deeply buried sandstones here that are only hope of finding a place we can put CO2 into the ground. If you go up north of Kingston, between Kingston and Ottawa, you can see an exposure of the Precambrian Shield, the Canadian Shield, and right above it, you find these Cambrian sandstones. So you can go to these places, you can visualize what's down underneath the ground that we can't see only through logs. So these sandstones, they overlay they're right down below they're immediately above the Precambrian Shield. That contact is exposed up near London, sort of up here between Kingston and Ottawa. Here, it's a kilometer or so underground. When you look at the rock types for the Cambrian, people take cores through these rocks. I've looked at the cores. What I'm showing here is a core log where mostly the things that are mostly dolomite are in blue and the things that are mostly sandstone are in yellow. And this bit of Cambrian section here is about 900 meters thick. It's about 90 meters thick. 900 meters is pretty good. It's not all the same. It's not a homogeneous tank. If you're somebody who's into flow modeling, what you've got to think about is heterogeneity. In modeling, you got to come up with some way of modeling fluid flow or gas flow through a very heterogeneous reservoir. This is coming out very blurry, but these are pictures of the rocks. This is this core. The different colors represent different rock types. Unfortunately, this is very blurry, so I'll just kind of skip through it. But the rocks aren't all the same. Some of the rocks are sandstone, some of the rocks are dolomites, some of the rocks are sandy dolomites, some of the rocks are dolomitic sandstones. If you're a geologist, there's lots of really cool structures in this stuff. If you're somebody who's interested in fluid flow, what you realize is that the rocks aren't all the same, they've all got different properties, they're all stacked together. And that's going to make fluid flow or gas flow through them complicated. Porosity and permeability measurements. lots of variability. The dolomites tend to be very low permeability and low porosity. The sandstones tend to be high porosity and high permeability. It's not a homogeneous tank, so you can't model it that way. Lots of interest in looking at the pores in the sandstones. I'll skip through this stuff. But I'm doing some SEM work now to try and understand the pore systems, how will fluids or gas flow through these things. Will the pores be modified through time as due to chemical reactions between the minerals and the CO2 that's injected into salt water generating carbonic acid. Lots of fun. You can play. Keeping in mind, we have to find places where we can store carbon dioxide. I mentioned that there are other places in North America where people are storing carbon dioxide, and it turns out some of those are in Cambrian age sandstones. Here, what I'm doing is comparing the porosity and permeability of some southern Ontario rocks in these yellow and orange and red colors in the background to places where carbon capture and storage projects are already underway in North America. We've got good rocks. It should work here. We've got decent porosity and permeability. In fact, we've probably got better porosity and permeability than a lot of places where this carbon dioxide, carbon capture and storage is already working. We've got this heterogeneity. The thickness of the sandstones, it pinches out. Remember, there's a big ridge that kind of extends down below us. The sandstones get thicker off to Ohio and New York. They get thicker off into Michigan, and they pinch out as they come up onto this old ridge that's underneath us. You can do cross sections that show how laterally continuous some of these sandstones are, whether they pinch out, whether they're continuous. What we find is that in the middle of Lake Erie, some of the sandstones can be 50, 60, 80 meters. Well, the Cambrian section can be 50, 60, 80 meters thick. Not all of it sandstone. The yellow stuff represents the sandstone dominated bits. Number 2, 3, 3A, and 5 represent intervals that have a lot of non-porous, non-permeable limestone. It's not just a big tank. So there was potential repository would be Cambrian age rocks. It's over 100 meters thick in places below Lake Ontario, Lake Erie. It thins and pinches as you come up north. So if you were to drill down 800 meters below where you're sitting, there are no Cambrian sandstones. They're gone. They pinched out by the time you get here, which means you can't just drill anywhere in southern Ontario. And we got good porosity and permeability. This didn't work, and this slide, remember this slide didn't work when I gave this talk in the geology department, but anyways, what you find is that the rocks are layered. They got a layer of sandstone, a layer of dolomite, a layer of sandstone, a layer of dolomite. The dolomite has very low permeability and porosity, and the sandstone has higher porosity and permeability. This is an outcrop between Kingston and Ottawa, where you can see this layering. The stuff that's sticking out of the outcrop are the carbonates. Stuff that's being recessive is the sandstone. Now imagine you put a well into this stuff. What you're seeing are the yellow would be high porosity sandstone, high porosity and permeability sandstones. The pink stuff would be dolomites. You've got what's known as permeability anisotropy. Things are going to flow very well that way, not so much. When you're modeling that, if you're going to model fluid flow through this stuff, you really need to take that into account. Multi-phase fluid flow through a heterogeneous reservoir. Do it or go home. So the repository is not just a single homogeneous tank. That's going to affect how how carbon dioxide flows through it. And yeah, you guys, if I'm talking to geologists, I'll say, hey, it's got bedding. For you folks, it's heterogeneous, it's anisotropic. Both in terms of flow properties and elastic properties, mechanical properties. We need to predict that heterogeneity in places where there's well control. There aren't wells everywhere in Southern Ontario. Somehow we need to predict that. Will the CO2 escape to the surface? Well, what we need are rocks that don't have porosity and permeability that act as a trap that stop CO2 from migrating to the surface. And when we look at what's above the Cambrian sandstones, we find a couple 100 meters of really non-porous, non-permeable limestone. There's a quarry in Picton, Ontario. They're quarrying limestone for cement. You see about 60 meters of limestone here. That's just part of the thickness of this unit. The reality is that when you map it in the subsurface, you see in places like over by Sarnia, it can be 300 meters thick. Down below us, it's maybe 250 meters thick. So this is a big, thick, couple 100-meter thick section of tight limestones that would be a good seal. Add on top of that, a couple 100 meters of shale. So we've got a very effective seal that's going to keep stuff in the subsurface. Geomechanical stability, not a lot of faults, but you got to worry about if you're injecting water into the ground or CO2 into the ground, where they're going to perturb stress fields and generate earthquakes. It's something to think about, and there's not a lot of data. There have been the Geologic Survey of Canada does monitor earthquakes in this area. Nothing that's ever felt. I grew up in Hamilton. There's a bunch of little earthquakes that have been detected there. They're just so small that you don't feel them unless you've got very sensitive kind of things. Basically, this is good news. It means that there's not a lot of faults in this area. So the area is tectonically stable, and geologists are going to have lots of terms for it. So this is what we're probably looking at in terms of carbon capture and storage. We'd have to do through several hundred meters of rock, some of it non-porous shale, some of it non-porous limestone, and we'll be injecting CO2 down into the Cambrian. Some of the sandstones within the Cambrian pinch out by the time you get to London. So we'd be here, there would be the shore of Lake Erie. Some of these things are continuous. Back in 2008, the idea was maybe to pump the CO2 down below Lake Erie and pump to an offshore platform. That'd be expensive. There's a potential to do it onshore along the north shore of Lake Erie. So what's coming up next? The bonus W, building a hub, building a place to put the CO2 is going to cost a couple billion. If you figure that a megaton, as a ballpark figure, a facility that can handle a megaton per year is going to cost about $1 billion. And we've got about 19 megatons of carbon dioxide that we want to sequester. It's going to be a huge outlay. We've got to have it done within the next 6 years. Can it be done? So it's a really urgent need to get this done. And so right now, there are people who are making plans to identify a spot, 1 or 2 spots, and do the testing. And that's what's coming up next. So I'll leave it there. Thank you. From the audience? Yes.
Can you have groundwater contamination because groundwater can be hundreds of meters over?
Yeah.
And if that's not the case, what about confined aquifers? Can it be affected?
Yeah, so the question was whether you can have groundwater contamination. If I go back here, go back 1 slide to this, the idea would be to pump the CO2 into reservoirs into rocks that are 800 meters down below us. Where we get our drinking water is tens of meters down below us. So there would be really no chance for the carbon dioxide from here to get up into our drinking water, that's tens of meters down below, us, unless it goes through some of these old oil and gas wells that are not very widespread, but they're around. But somebody's gonna have to check that.
Other questions?
Yes, so judging by the scale of carbon dioxide produced every year, do you think the storages would be enough to what they call to store all of this carbon dioxide?
So your question is about volumes?
Well, yeah, because we are producing a lot of carbon dioxide.
Yeah. So the question is, are there enough porous sandstones here in southern Ontario to do that? And that's where I say, I'm a geologist. I have to give the information to the engineers who are gonna be able to figure that stuff out. And that's, what I need to do is when I'm working with the engineers is I have to make sure that they don't model it as a homogeneous tank, which is what people like doing. But that work needs to be done. And there needs to be testing to see if, if the models conform to reality and that kind of stuff. But that's a very valid question. And right now it's unknown.
How are you planning to transport the carbon dioxide from their place of emission to the storage place?
Yeah, so the above ground transport, as a geologist, I tend to focus on what's underground, but that's one of the slides at the beginning, I showed where the pipelines are. Those pipelines get used for natural gas, they get used for oil and various other things. Those pipelines apparently can take slugs of CO2. So apparently you can have a pipeline that normally puts natural gas from Alberta, taking it out to Montreal or whatever. And apparently you can't put slugs of CO2 into it, but those are the pipeline people. But existing infrastructure is critical. I think I heard the number saying that it costs about $2 million if you want to build new pipeline, it costs about $2 million per kilometer of pipeline that you want to build. So if you want to build pipelines that are going to be 50 kilometers long from your point source to someplace else times 20, it gets to be really expensive. So existing infrastructure is what people want to use.
As a person who studied pipeline design, actually, so majority of companies, they want to what they call the economy is a big factor for them. Do you think they'll put that much money to transport carbon dioxide?
So so the question was whether the companies will afford this, right? We'll spend the money on it. And partly the issue is that even a company like Stelco or Dofasco, these Canadian steel companies, they can't do it by themselves. The cement plants can't do it by themselves. So somehow they've got to pool the resources. And one of the things that's happening stateside, it's happening out west, it's happening in other parts of the world, are subsidies to make, government subsidies. And it sounds horrible, you're going to subsidize fossil fuel emissions, right? And keep that going. But the reality is, like I was saying, we need steel to build windmills. If the steel mills in southern Ontario go out of business, and the steel mills in the US or China or some other place, steel mills in the US are getting they got big tax breaks for carbon capture and storage. Here, we don't have that in place. So that's a big question too.
Okay, I think we'll cut it off here. Feel free to come up to Bruce for questions if you wanted to have more discussion afterwards. Apart from that, thank you very much for giving us the call.